Hi everyone, in this video we look at geometric series. So a geometric series is the sum of the consecutive terms in a geometric sequence. And if you recall, in a geometric sequence, all consecutive terms have a common ratio r. So what does that mean? Well, it means that if the first term is a, the second term would be ar, the third term would be ar squared, the fourth term would be ar cubed, and so forth. So to get and the nth term would be a to the power of n minus 1. So one of the things to note here is that here if we divide any term by its preceding term, you get this common ratio r. So to get the next term, if we know, like the third term, to get the fourth term, we could just multiply the third term by the common ratio if we know it. So in a geometric series, we're just going to add the terms in this sequence. So we could have a plus ar plus ar squared plus ar cubed plus ar to the power of n minus 1. Now, there's a trick for summing this series. It's kind of similar to what we use to sum arithmetic, to come up with a formula for summing arithmetic series. Let's say if this value is s, let's write underneath it, let's write out the same sum, only let's write it a little bit differently. Let's write it as a plus ar plus ar squared plus plus ar to the power of n minus 2 plus ar to the power of n minus 1. Now, all that I did was I just wrote out the exact same series below. Now, let's think about what happens if I multiply this series by r. I have r times s. I would using the distributive property, I would multiply every single one of these terms by r. So my first term would be ar. My second term would be ar squared. My third term, let's see here. My third term would be ar cubed. Whoops. Would be ar cubed, and then I would have ar to the power of n minus 1, because I've got an extra factor of r there, so I have ar to the power of n minus 1. One more factor of r, if you add another factor of r to n minus 2, you get r to the power of n minus 1. And the last term, we're just going to have ar to the power of n, where we've just increased the exponent by 1 for all of the terms in the series. So let's think about why this is useful. Well, if I do s minus r times s, so if I take this series and I subtract this series below, well, look at what happens. I've got a minus 0, which is just ar minus ar, which is 0, ar squared minus ar squared, which is 0, ar cubed minus ar cubed, which is 0. I would have ar to the power of 4 minus ar to the power of 4, all the way up until I have ar to the power of n minus 1 minus ar to the power of n minus 1, which is 0, and then I have 0 minus ar to the power of n. So I would have a minus ar to the power of n. So why is this useful? Well, here, notice that I can common factor s out. And I have that s times 1 minus r is equal to let's factor a out. Let's common factor a out of these two terms. A times 1 minus r to the power of n. Now I can divide both sides of this equation by 1 minus r And what I'm left with is that s is equal to a times 1 minus r to the power of n, all divided by 1 minus r. So if we have a geometric sequence, or sorry, a geometric series rather, if we have a geometric series and we want to sum all the terms in that geometric series, the sum is equivalent to the first term times 1 minus the common ratio to the power of the number of terms in the series, all divided by 1 minus the common ratio. And here we have that the common ratio cannot be equivalent to 1. Because if the common ratio is equivalent to 1, we have division by 0 in the denominator, which is undefined here. Actually, it would be indeterminate, because we'd have 1 minus 1 to the power of n divided by, which is 0, divided by 1 minus 1, which is 0 as well. So that'd be indeterminate, not undefined. But we still need the restriction that r cannot be equal to negative, or it cannot be equal to 1.